So our variable of interest is the number shown by the spinner. Okay, X is the number shown, number on the spinner. Okay, can you please find the population mean and the population standard deviation using your graphic calculator? So our variable is number on the spinner. And this one, the population is very small. In real life, the population is very big. Like number of young adults. So the population is very big. Okay. So can you please tell me what is the mean? What is the standard deviation of the population? Mean 2.5. Standard deviation 1.12. You know the formula, how to get it correct? So I'm not going to go into the formula anymore. Okay, so now look, so now we are going to get a sample from this population. Okay, we are going to do sampling. Okay, so how many possible sample can I get sampling? The sample size is, sample size, in this case, we always use n, and in this case is 2, right? And the sampling must be random sample. So can you please tell me how many possible sample can I get? Exotic sample. How many sample can I get? My first question. Are you sure? You get exotic sample, that means all the possible sample. How many possible samples can be drawn from the population? 7. So we say that the random sample must be what? Every member in the population must have an equal chance to be selected, correct? So if I select one already, I spin once. So when I spin the second time, will I get the same number? I can get the same number. Correct? Am I right? So how many possible samples can I get? So the first spin, I can get 4 possible answers. And the second spin, I also can get 4 possible outcomes, correct? So n is a multiply, correct? So how many possible outcomes can I have? Sample, 16 samples. So you can imagine if you have hundreds in the population, how many possible sample can you get of size 2? 100 times 100. So in real life, it is not possible for us to get the exotic samples. Exotic samples, that means you get all the samples into consideration. Are you clear? That is the meaning of exotic samples. You get me? If I want the sample size 3, in this case, how many possible sample can I get? Four times 4 times 4, 64 samples. Am I right? Okay, so that's why in this discussion, we try to give you a population which is very small to let you see the relationship between whatever we want to discuss afterward with the population. Do you get me? Okay, so now in this case, what is the variable that we are interested in? Are we interested in the sum of the sample or the mean of the samples? Read the question. Mean of the sample. So you see, first, okay, mean of the sample. So now in this case, our parameter of interest or our variable here, variable we want to talk about is the mean of samples. And I put 2 there, that means the sample size is 2. Okay, so now we are going to list out all the possible samples. And each one, we are going to find the sample mean. So now we are going to list out all the 16 possible samples. So you draw 16 lines, 16 columns. So the first one is you get 1, 1. Then you count the mean. This is the first spin. This is the second spin. So this is your first sample. 1, 2, 1, 3, 1, 4. So everyone you count the mean. Then you go 16 of them. So we are doing exotic sample for this situation. 2, 1, 2, 2, 2, 3, 2, 4, 3, 1, 3, 2. Three, 3, 3, 4. 4, 1, 4, 2, 4, 3, and the last one, 4, 4. Every sample you count the mean because our variable is sample mean. Then you build a probability distribution table for the sample mean. Each one have an equal chance to be selected, so it's 1 over 4, correct? So each one, the probability will be 1 over 16. Am I right? There are 16 outcomes. Okay, faster. Count. You know how to count the mean, correct? Add up, divide by 2. Yes, Muklis, do. Then build the probability distribution for the sample mean. The first one, the mean is 1. The second one, the mean is 1.5. The third one, the mean is 2. The mean is 2.5. 1.5. 2. 2.5. 3. 2. 2.5. 3, 3.5, 2.5, 3, 3.5, and 4. So build a probability distribution table for sample mean. Mean means the average. Okay? So the lowest mean is 1, then go 1.5, then 2, 2.5, 3, 3.5, then 4. Okay, can you count the probability for each one? 1 only appear once, so 1 out of 16. All right? 1.5 appear how many times? 1, 2, 2 times. Am I right? So 2 out of 16. 2 appear how many times? 3 times. So 3 out of 16. 2.5 appear 4 times. 4 out of 16. Right? 3 appear how many times? 3 times. Do you see from the table, you can see the symmetrical part of it? Yep. Okay. So can you please now listen here? I'm going to write a symbol and tell you how are you going to read this. If I write like that, so what do you call this table? What do you call this table? Andy mana? Siti mana? What do you call this table? Nama. Probability distribution table for what? Sample mean. So your variable is sample mean. So if you want the mean of samples or you want to put sample mean also can. So now look, if I write like that. So this, do you know all this? Okay, listen all this here, I call it the population of sample mean. Do you know that? This is the population of sample mean. This one is the population of X. This one is the population of X bar 2. Understand? So when you talk about population, if I write like that, so how am I going to read this? So this is the mean of the sample mean population. I add in the word population some more. So that's why I can use the mu. Do you get me? Can you please key into the calculator this table and get the answer? I can tell you the answer. 2.5. Huh? This table. Key into your calculator and get the mean. And this one, if I write like that, this one means the standard deviation of the sample mean population. So your variable is the sample mean. So you have to be very careful. When you have all these, the bottom there, the subscript, superscript is up. Subscript there tell you the variable. Understand? Okay, so this one, do you get 2.5? Yeah, what is this one? .79. Some more? 1. Okay. Can anyone tell me why the standard deviation of sample mean population is much smaller than the population of X standard deviation? Okay, you don't want to answer me, never mind. So my variable is the X. The mean of X is 2.5. The standard deviation for X is 1.12. Thank you. 1.12. Okay. And if I, 1.12. Okay. So if I plot the distribution of X, I will get 1. Okay, I put like that. 1, 2, 3, 4. This is discrete, correct? So I do the spike diagram. So I do the spike diagram. Here is 1/4. I got this. I got this. I got this. And I got this, correct? Yep. That is how the distribution, correct? Am I right? So now I talk about my sample mean distribution. The sample size. This sample is drawn from here. This is the sample mean. Okay. The n is equal to 2, the sample size. Okay. So we have the mean of the sample mean population is equal to 2.5 also. And the standard deviation is equal to 0.791. Right? And if I plot the distribution of the sample mean, so I got my 1, 1.5, 2, 2.5, 3, 3.5, and the last one is 4. Okay, the first one is 1/16. 1.5 is 2/16, is it? Okay, 2/16. 2 is 3/16, correct? 2.5 is 4/16. And 3 right? So what is the shape of the distribution of X compared to the distribution of sample mean? This is symmetrical. This one. And see the relationship between this one. Why the standard deviation of the sample mean is smaller? Compared to the sample mean population, standard deviation is smaller than the standard deviation of the population where the sample is drawn from. The reason is because each sample is a representation of the population. So if we count the mean of each sample shouldn't vary much, correct? Am I right? It's a representation of the population. The variation of the mean should be close to the population. Am I right? And this one, all I talk about here will make up what you so-called your central limit theorem. Central limit theorem. That is in your 9C. Can you please read your 9C first before we go further? So the investigation there, it takes a long time, so we are not going to do that. You take exotic sample, okay? So you can learn up how to do the things, yeah, so that you can do it for your folio. Okay. So maybe you want to read through 260, page 260, talk about the spread. Okay, 261. Then you go to central limit theorem. That is page 263. Okay, maybe we can go to page 264 straight away, everyone. I will read it to you. Okay, so that is a theorem. Okay, central limit theorem, listen here. This is a theorem. When you talk about theorem, that means someone have gone through a lot of examples. They have seen the pattern of it, then they come out with this theorem. Are you clear? We only see one example, so we cannot say we come up with the theorem. All right. So those who want to come up with the theorem, they have proved the relationship of this with many examples. Are you clear? And they come up with this theorem. Okay. So I'm going to read the theorem to you. Suppose X is a random variable, which is not necessarily normally distributed, whereby this case, is my X normally distributed? No. So not necessary. Do you know which page I'm talking about? Page 264. So suppose X is a random variable, which is not necessarily normally distributed. True or not? This is not normally distributed. It can be not. Okay, not necessarily normally distributed. X has a mean of mu. So for me, I will put mu X at the bottom. So maybe in your textbook, you just put mu X like that. Mu, that means the standard deviation. It's good to put X there, down there. And a standard deviation of this one. For sufficiently large n, n is the sample size. Okay, the distribution of sample mean. This is called the distribution of sample mean. Of size n is approximately normal with the mean. So the mean, how we write the mean? This is how we write the mean. with the mean equal to the population mean, and the standard deviation is equal to the population standard deviation divided by square root of n. Isn't it? You try 1.12 divided by root 2. Do you get that? The larger the value of n, the better the approximation will be. The larger the larger the value of n, the better the approximation of will be. What approximation am I talking about? Can someone give me the answer? What approximation am I talking about? You see, this book doesn't give a good. What approximation am I talking about? What approximation am I talking about? I take so many times already, still no one want to answer me. What approximation am I talking about? I'm trying to approximate the population mean. So that means the better the approximation will be. This approximation is talking about the sample mean. The mean of all the samples will be very close to each other. It means that the standard deviation of the sample mean distribution will be smaller. That is the meaning of better the approximation will be. Are you clear? Did you write down? I didn't write down. You better write down. Huh? You can write down in your textbook with pencil. What do you mean by better approximation will be? So this is a central limit theorem. So I'm going to phrase this central limit theorem in an the questions, the statement said the larger the value of n. What do you mean by the larger the value of n? The bigger the sample size, the better the approximation will be, means the smaller the standard deviation of the sample mean population. This one will be smaller. Are you clear? Okay, so this is the central limit theorem stated by your textbook. Okay, I'm going to state central limit theorem as, if you go and refer to other books, they will state it as another way. They say, and if you read the following part, we note that, okay, can you please look at the pointer on page 264 first? Many texts suggest a rule of thumb. If n greater than or equal to 30 to indicate n is large enough. That means you want to get, like for example, correct? For example, for this example, okay? That's why it's very difficult for you to figure out. We have to go through. For this example, how many members do I have in the population? Only 4. So out of 4, I take 2. You think my sample size is large enough? Definitely is large enough. But if I have a population of 1,000, I take a sample size, the sample size is only 2. That means each sample I only pick 2. Do you think it's large enough? may not. Correct? So that's why statisticians give a thumb of rule. They want to give minimum 30. So in real life, your population is very huge, okay? Like I want to talk about teenagers in Malaysia. Do you know how many of them? It's impossible for me to know the mean height. So they are using sampling. That is what we are going to learn later on. But in your textbook, listen here. So textbook question and real life situation are totally different things. Textbook question always tell you the population mean. In real life, you won't be able to know the population mean. You only predict. So that is one fact that you have to bear in mind when you write your folio. You are trying to predict the population mean based on the sample mean and based on the central limit theorem. Are you clear? Textbook questions are different, huh? They give you. Okay, now. So they say many texts suggest a rule of thumb. Maybe when you write in your folio, you also can write this. N must be greater than 30 to indicate N is large enough. So you can explain when you are writing your folio, you can explain why your N is large enough because by thumb of rule. That's it. But however, this value depends on the normality of the original variable X. Okay, I'm going to explain this statement. Listen, by going to the central limit theorem just now. Okay, my central limit theorem, the first thing is I want to say, if the population is normally distributed, like for example, we talk about naturally occurrence thing, definitely is normally distributed, correct? So I will say for any sample size, the sample mean distribution for any population. So can I just add an X here? If the population X is normally distributed for any sample size, the sample mean, so is talking about here, is also normally distributed. But with smaller spread. So that will explain the first point that, however, this value depends on the normality of the original variable X. So if my X is normally distributed, my sample mean distribution sure will be normally distributed. It doesn't matter how, whatever sample size you take. So now, based on this statement, so usually when I talk about central limit theorem, I like to break it with my population is normally distributed, what happened? Instead of just lump it in one. Okay, so now I'm going to give you two distribution, two graphs. You tell me which is X and which is XN. This is my A. Okay. Okay, which is which? Which is X? And which is X bar to sorry, which is X no bar, and which is X bar maybe 10. So you see my N is not X bar 10. Why? Okay, want to give the answer? You just have to base on my statement, Kennedy. A is X. So B will be X bar 10. Okay. Why? Because the spread of B is smaller. See or not? Both are normal. You get what I mean? So that is the first thing. Okay. So I'm going to test you on the statement. The larger the value of N, the better the approximation will be. The larger the value of N, the better the approximation will be. Okay. Should I? Okay, so now you look. I also have two. Okay. Both are normally distributed. Okay. Which is X bar 10 and which is X bar 20? Why? $15, $18. Sorry. Thank you. Okay, who can answer me? Which is X bar 10 and which is X bar 20? Why? B is smaller spread. So, yeah. So how are you going to answer this in a better way? Because the larger the value of N, the better the approximation will be. So you have to compare the N. Faster. Anyone? You keep quiet. I tell you in the exam, you are going to, you better say out your answer. Nick mana? Woi, Amira mana? Cakap, cepat. No, the problem is I tell you statistic if you don't talk, if you don't give me the explanation, wait for my explanation, correct? You are going to, especially when you write your folio. That's why I go very slow, you see. Quick, 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 quick. Abika, want to try? You have to make a comparison because in that statement, the larger the value of n. So now your focus is on n. So you see or not? That is how you analyze. Okay, B is for x bar 20 because 20 is greater than 10. So you will give a better approximation of the mean. Correct? So the spread will be smaller. So I choose B as x bar 20. You compare the number first. So I want to answer this question. I have to base on the statement, the larger the value of n, the better the approximation will be. Right? Hello? This is the central limit theorem about the population is normally distributed. So the sample mean will definitely normally distributed regardless of their sample size. Are you clear? But with a smaller spread. Got it? Now, if I ask you this question, if my sample size is 1, what do you think? If my sample size is 1, that means it's the population itself. Am I right? Am I right? So you won't be surprised they will ask questions like that. Okay, so now I want to talk about the second part. That means if the population that is the X is not normally distributed. Okay, so now we are going to use a thumb of rule. N must be greater than 30 to indicate large enough, correct? However, the value depends on the normality of the original variable X. So if the population X is not normally distributed, okay. Okay. If the population X is not normally distributed as n, that is the sample size, increases, the sample mean distribution will approach. P-A-P-P-R-O-A, approach normal. distribution. So in this case, you can use the thumb of rule n greater than or equal to 30. As what our case here. Okay, I'm going to go to our case there. Hello? Look at. Can I? Here. See or not? Is this normally distributed? No. But is this normally distributed? Yes. So that is the central limit theorem all about, the two part first. Okay. Now, I want to test on you. Okay. If this case I want to test on you is, I got this, A. Then I got this, B. So my question will be the same. Which is X, the population, and which is sample mean? Distribution. Why? So what will your answer be? Kevin, answer? Okay, 57. Sample mean. Why? You straight away die. Right? We was in this case, you are not talking about the spread. You are talking about the normality. See or not? You give me the wrong reason, you get 0 straight. A is not normally distributed, but B is normally distributed. Therefore, B is the distribution of the sample mean. See or not? Okay. This one is skewed. A is skewed left, correct? So in this case, you are not supposed to talk about the spread. You are supposed to talk about the normality. So you see your focus. Okay, now I try another one. These are all the questions that you will see in your SAT 6, okay? How I want to phrase this is up to me. Okay, now if I give you like that, given a Is sample size 10 large enough? Because we said by thumb of rule, n must be greater than 30, correct? So now I'm asking you, given x bar 5 is the shape of the distribution is like that. Is sample size of 10 large enough? Why? Why? You see enough? Okay, we say, is sample size 10 large enough? The answer is a yes, because 10 is more than 5. So with the sample size of 5, the distribution of the sample mean is already normally distributed. So now with the sample size of 10, it is definitely normally distributed, but with a smaller spread. If you want to explain further. So that is a very important part of the two central limit theorem. And the second part of the central limit theorem will be, first, the first part of the central limit theorem is talk about the shape of the sample mean distribution. All very much depend on the population distribution. Clear? The second part of the central limit theorem is talking about the mean of the sample mean. That is how you read, is equal to the population mean. And the standard deviation of the sample mean is equal to the standard deviation of the population divided by square root of n. Why? Because the mean of each sample should be very close to each other, because they are the representation of the population. The larger the sample size, the smaller the spread of the sample mean distribution. Okay, I overshot the time. Okay, you see, I want to finish up the whole thing. The reason is because the thing must come as a whole. Okay, so now you go back, you try to do exercise 9C and 9B and 9C. Okay, so this is a very important theorem. You can go to YouTube and read